So for the second machine learning for discrete optimization or optimization talk of the day, I'm happy to introduce Kevin Tierney. Kevin is a full professor in decision and operation technologies at Bielefeld University in Germany. He holds a bachelor's from Rochester Institute of Technology and a master's in computer science from Brown, and his PhD is from the IT University of Copenhagen in Denmark. He was previously assistant professor at Paderborn University, also in Germany, and he has done a lot of work on topics related to the first talk as well, in algorithm configuration, machine learning for solving optimization problems, and logistics supply chain applications. And his work on the neural large neighborhood search approach has won the Distinguished Paper Award at the European Conference for AI in 2020. So we're very thrilled to hear about the latest developments in this space.
Yeah, thank you very much. So I'm going to talk a little bit about search heuristics and solving combinatorial optimization problems with reinforcement learning. But yeah, I mean, their previous talk was also really interesting, and I almost felt like I should have pulled out an algorithm configuration talk, but we're going to do something else instead. So the outline for the talk, first, I want to try to motivate what I'm working on a little bit, but also manage expectations. It's a developing field, but some people in OR may be disappointed that we don't always outperform state-of-the-art OR stuff. On the other hand, from an ML perspective, things are moving along really nicely. And so we'll try to get started with how we can do routing problems with machine learning. Although I would note that the techniques here that I present are general. We've mainly used them on routing and some scheduling problems, but in principle, they should work on any kind of combinatorial optimization problem. But again, we'll manage your expectations in a moment. And I'm going to introduce 3 different methods, and I promise to stay on time with that. So the first one is neural large neighborhood search. The second, efficient active search, and the final one, simulation guided beam search. They're basically all different ways of doing search on a problem where you've learned some kind of model that can make decisions. And I'll show you what that means in a moment. And thanks to all the co-authors on this work. They're listed down here and throughout the slides. So our goal really with this work is to combine machine learning and optimization somehow to move towards automated development. Like basically what we'd like to do is solve optimizations through reinforcement learning. And so that has a few advantages and disadvantages. The first advantage really is that at least my hope is that it lowers the barrier to entry, that we essentially turn OR problems to some extent into more of a data science problem in the thinking that you have a lot of data scientists out there. They don't really know, like your average data scientist doesn't know a whole lot about OR, but if you were if you could give them a tool that they could use that's in their data science language to some extent, maybe then they can actually, apply OR in places where it's not being applied right now, especially, like in small companies that don't have the money to hire OR consultants and don't have the know-how themselves, places like that, maybe nonprofits who also don't have those abilities. Another advantage, though, that just completely ignoring the barrier to entry is that you can customize heuristics and get better performance for the type of instances at hand. And that actually also extends from the previous talk is in this sort of field of algorithm configuration, where we really are trying to make algorithms and approaches that work extra good at certain instances. And this is something that, there's lots of different techniques now that can do this, and that for different instance groups can sort of improve the performance of a general algorithm on a particular data set. I mean, even for MIP solvers like Cplex and Gurobi, this works pretty well. Just to tune them for specific instances, you get better performance. But there are some disadvantages. So, I mean, the things I'm working on right now, I don't want to claim that's like, it's not perfect. Especially the learning phase is very computationally expensive. You're going to need at least a GPU with the methods we have right now. And you're going to need a few days, maybe even a few weeks, depending on what you're doing. Now, if you apply this kind of algorithm over a long course of time, then maybe that's not so bad, but it's a disadvantage for some people. And a bigger disadvantage when we think about kind of trustworthy AI principles, the algorithmic interpretability of the methods I'm going to present here is extremely low. If we compare it to sort of handcrafted solutions or like, traditional OR heuristics where we kind of know how they work, at least to some extent, and maybe know roughly why they, build the instance, they build a solution that they build. With the methods I'm going to show you today, we do not know why they do what they do, and we know they make mistakes sometimes that are really stupid, and we don't know why. So I think this interpretability aspect is a huge open area that I fully admit is a huge problem right now. So let me further manage your expectations. Feel like, a lot of the times this machine learning for optimization is kind of trying to sell you this Lamborghini over there. You want to query a model, it's going to spit out an optimal solution, can solve any combinatorial optimization problem the user gives you, can scale to any size. The reality, it's not so bad because okay, I put in an old Camry. I used to have like a car like this, and actually they were pretty reliable. I liked it. It was a fun car. So, you query a model, you get a solution. It's maybe not so good, but it is a solution. And then sometimes it is really good. We can solve simple classes of problems that have like easy side constraints. So let's say that the techniques I'm going to show you, even if I say they're general for combinatorial optimization, it's not entirely true in a way. If the problems have too many side constraints, like no one's really done those. And you kind of need let's say a nice problem representation, like you get in many easy routing problems and in some other problems. The scaling, let's just say it's not great so far. There are some techniques out there that are working on it, and there's been good progress on scaling, but these techniques definitely don't scale the way that, let's just say, sort of a standard genetic algorithm or something does. Okay, so let's think about how to construct a solution and where we can use machine learning to help us. So if we're solving the capacitated vehicle routing problem, and I'm just going to assume that everyone kind of knows about it, our goal is to decide where to go next. So if I have a partial solution here, and I have a node here that I have to decide where do I go next, right? Like I have three basic options. I find someone really good at solving VRPs, right? There's a lot of people who actually can do this, dispatchers at a lot of companies, and they're pretty good at it. You could go find one of those people and ask them what to do next. You could ask a traditional OR heuristic. So traditional in quotes here, it sounds like, like artisanal water or something, some kind of special OR heuristic. But this is just what we've been doing for a long time. The field has gotten very good at it. And the final option is to ask a deep neural network or some other machine learning algorithm. And today we're going to ask deep neural networks. So the deep neural network architecture we use is basically, it's in essence a very small version. It's a transformer architecture. We have this encoder decoder. It's not really that different from a high level view from all these NLP models, ChatGPT and these things. At a high level, it's very similar. If you get closer to the details, things really start to change quite a bit. But at the high level, you can understand it works like this. We have an encoder. It takes a problem instance and basically makes this thing called an embedding. This is just an n-dimensional vector. This is basically just taking an instance and trying to turn it into some kind of number that the network can understand. And hopefully similar instances have similar vectors in this embedded space. The decoder takes an embedding and a query, essentially which node to search from, for example, and decides what to do next. So here we get a probability distribution, which will be shown throughout this presentation as these sort of purplish bars. We can sample an action, take the argmax or whatever, apply that. And so here, for example, you see we have the maximum probability down here. So we take this node, we sample then the decoder again, and so on. And there's a whole bunch of things you can do to ensure feasibility or at least encourage infeasibility and so on. And by doing this, though, you get a full solution. Now, this is a nice architecture because it accepts variable sized input. So some of the papers out there, the older papers didn't have this. This particular architecture is really nice. It's essentially a recurrent neural network structure. You can take different problem sizes, put them in there, and that's really great. And if you want more details on sort of this, I encourage you to basically look at the papers or look at the code, because the presentation, like 25 minutes would be too short to really describe everything anyway. Here are a couple papers, especially on these architectures. So Cool et al., Attention, Learn to Solve Routing, and from Kwan, the POMO paper. Both of them have source code that is really nice. So then if we use this encoder-decoder architecture, the basic question we have when sort of doing this kind of research is, do we want supervised learning or reinforcement learning? If I do supervised learning, I have one, sort of the pro there is that I can use optimal or very good solutions, which can be very good for training. But the con with supervised learning, is a big kind of downside, I think, is that you need a traditional OR approach. So in other words, you actually have to sort of write a whole heuristic or MIP model for the problem, use that to train your model, and then you can solve things. And I mean, the question, of course, is like, why wouldn't I just then use what I already wrote to solve the problem? Why do I need this learning method, right? Like, seems like a lot of extra work. So a lot of people now are using reinforcement learning, myself included. The pro there is that we don't need an existing algorithm, but the downside is that the approach kind of starts out pretty stupid and has to kind of figure out a way to solve problems and become smart. The loss, or really reward function that we use, is just the objective function of the solutions. So it's actually pretty simple when you consider RL in general. What we do is on that side of things, not too complicated. So let's just look at a summary so far of how we would generate a solution for the CRP here, so CVRP. I'm going to take the nodes and run them all through my encoder. Essentially, this is making these features. So I have some vector H, which describes sort of the whole instance. And I have vectors HI, which are some kind of embedding of each node. So each node has its own vector, and I can average them or sum them up or whatever and get a vector H that aggregates everything together. Now, if I want to sort of find out where to go, I can put all of these nodes through the decoder along with the information about the instance, and I get some kind of score out. So for each node, I take those scores for each node, run them through like a softmax layer, which is basically going to build a probability distribution over the nodes. And I see here I have one that's the highest probability. I take that one. So you'll notice we often just go with the argmax, but that's not always going to be the case. And now you rinse and repeat. Just do that again and again. You have a full solution. You can mask the node that you already visited and then essentially hiding it from the output. Some methods update their embeddings. It's sort of like, you know, because in a sense you have a new instance now, right? I mean, you can kind of imagine like a phantom depot or one of these virtual depots or something that encompasses this whole thing. So you could update your embedding. Some methods do that. It works sometimes it doesn't. I wish I knew when or why. I don't think we know that much about it yet. Okay, but the problem here is like I made a solution, and the question is like, what do I do if the solution I generated isn't good? Well, I can sample. I can sample from the network's output space, build more solutions. This is great because it's highly and trivially parallelizable on the GPU. But the con are the quickly diminishing returns. Like this, you sample for a half a second and you've pretty much found the best solution you're going to find through sampling, right? Because it's dumb. It's just random. So we propose to basically apply search on top of the model. So some kind of high-level heuristic, we're thinking along the lines of meta-heuristics here. This has, the pro is that really there's a lot of techniques out there that have good performance that we've found. One downside, though, is that if you do use the CPU in your search, you do have some latency penalty, essentially, to move between the GPU and CPU. That's not so fast right now. Maybe in the future it'll be better. The new Macs seem to be quite good with that, but that's a problem. So it's nice to try to stay on the GPU, and that can limit what kind of search procedures you can use. But it's really parallelizable in most cases, so that's really good. And this presentation is all about the search. So one more sort of background slide, and then we get to the search procedures. Something that sort of, your sort of standard discrete optimization person might not realize with this kind of method, a huge advantage of using the GPU is your ability to solve batches of instances. So if you're given a set of instances to solve, like there's a company nearby us here in Bielefeld, Germany. They have to solve quite a few routing problems every week, several hundred. And you can just, if you had a nice method to run them in parallel, you could basically solve those way faster, right, than if you solve them one at a time. Now, obviously, CPUs these days have a lot of cores. You can parallelize across CPUs, but GPUs parallelize way better. And so GPUs offer a really interesting way of potentially solving lots of instances fast. The problem is, though, that the way they parallelize is not conducive to our standard OR technique. So something like branch and bound, just at least I have no idea how you would get that thing onto a GPU, and I don't think anyone out there really has any good proposals right now for how to do it. But deep learning parallelizes great onto the GPU. And so if we use a deep learned model, we can parallelize that out and make decisions across multiple instances, essentially in parallel, which is really nice. So the first method I want to talk about is neural large neighborhood search. It's not too complicated. If you know LNS, you probably already can figure out how this works. If you're interested in reading the paper, QR code's up there. There's also these slides that will be posted somewhere online. The source code's available from my PhD student, Andre. He posted on GitHub. The insight is basically, well, we know LNS is good at solving routing and scheduling problems, right? So why don't we just use a neural repair operator to construct a solution with a deep neural network? So how it works, you have the destroy step. So say, well, let's start, I have a solution here, right? I start with a solution. In the destroy step of the algorithm, we take a piece of that solution and we're basically going to delete that part of the solution. So that's what destroy means in this context. This is called a point-based destroy. You can use any operator and they're really easy to make. So I wouldn't say this isn't like a huge hurdle to anyone who knows about this kind of stuff. Even, students can figure these operators out. You remove that piece of the solution, shown in gray now. So we have no arcs on these nodes anymore. The solution is not complete. In the repair step, now we're going to rebuild the solution. But notice how we have some part of the solution is fixed, and the rest is sort of just left open. And so I'm going to query my model, and it's going to give me the probability distribution. I'll take the argmax, which I guess I didn't. Let's just say I sampled it here. So I sample it and I go up there for some reason. The probability distribution also changed, which shouldn't have. So I go up there and I'm going to just keep querying the model from the place I was last. So I'll start over here now and keep going. And so I make this route and I eventually get to a part of the solution that was already fixed. Now notice I'm not done yet because there's still an arc missing. And so I restart the rollout at the depot until all the routes are complete. And you just iterate this destroy and repair until you have some kind of convergence, right? The solution doesn't improve anymore, or you just get, you hit a timeout, whatever. That's basically the method. There's not many more details than that. And it works pretty good. Let me show you some results. There's more in our paper, but I think these are the interesting instances. And so these instance sets are somehow sort of modeled on real world data, but I mean, I'll admit that, this isn't from a company or something. So it's still somewhat random. We have in this column the gap from NLNS to UHGS. So UHGS is from Thibaut Vidal. There's a newer version, HGS, which we'll use later, but this is a bit of an older paper. So we used UHGS. It's a very good genetic algorithm-based approach for solving the CVRP. And basically, we can't beat it. So, if you were expecting me to come here and beat like some state-of-the-art method in CVRP, I'm sorry, I've disappointed you, and you're now unhappy. But the good news is we can compete very competitively with LKH3. And of course, LKH3 is a great heuristic, right? I mean, it's really, really good. So I'm very happy that NLNS actually, we're able to learn very effective heuristics that beat LKH3 in most of the cases that we have. There's more in the paper. I mean, furthermore, one of the important things, of course, to show is that, is the improvement we're seeing due to the model or just due to the paradigm LNS? And in fact, we compare against sort of a standard LNS approach. Of course, anyone can argue, you can make any kind of nice LNS, but basically a standard LNS doesn't really, it does decently well, but doesn't do that great on these problems. So NLNS wins. So this approach performs quite well, even though it's fairly simple to set up. However, a downside of NLNS is that it's kind of domain specific, right? You have to make this destroy operator, the repair operator. You have to sort of make as well that to work in this sort of partial solution environment. We'd like to have a method for search that's a little more domain independent, and that's where we came up with efficient active search. So first, a little background: active search. Bello et al. Proposed this method. Basically, what you do is you train a model using reinforcement learning. And then in the testing phase, when you're getting new instances you haven't seen before, what you're going to do is when you make a solution, you can now use the quality of that solution to fine tune the model and output a new solution. So you're going to adjust the weights for each after each solution or set of solutions that you generate, and so that your model can work better. Essentially, you just continue the reinforcement learning for a specific instance. Why is this not good? It's expensive. Fine tuning the model in this way takes a lot of time. So the question we had was, how can we make this faster? And this is iClear paper from 2022. Again, use a QR code or look at the code, the source code. Basically, there's 3 different proposals we have, and the insight is for all of them essentially the same. Why adjust all the weights when we can just adjust some? So the contribution here is that we just are going to change a small subset of model parameters, basically backpropagating and continuing the RL during the solution phase, during the testing phase. And this actually works quite well to avoid the extra computational work, but still gets us performance gains. So the first strategy is the added layer updates. So you just add an extra layer to the decoder, and you're only going to update this layer during the search. Now, why is this great? Is that you only have to compute gradients up to that layer. So, I mean, you can put it in a place that basically, right at the start or something, and then or after the first layer, you don't have to do too many gradients. Most network weights are shared across the instances. And most network operations can be applied identically across instances, which means you can really highly parallelize this method. Now, the second version is embedding updates, which is, I mean, it's the same idea. You just put it in the essentially in the encoder here between the embedding and the decoder. Instead of, now you don't have to touch your decoder. You only have to change your embeddings. I don't know which one works best. I mean, sometimes one works better, sometimes the other. But basically, both of them have the same kind of advantages and very few disadvantages. We have a third strategy as well, which maybe I'll just skip for time, but it's in the slides online if you're interested in it. It's cool because it doesn't involve backpropagation. So with that method, so this method, that's basically it. That's all you have to do. I'm going to show you results in a moment. The reason I'm not showing you them yet is because you can combine this with a beam search method called simulation guided beam search. And this is with a whole bunch of great colleagues at Samsung SDS in Korea. We've had really nice collaboration with them. A lot of smart guys over there. The insight here is that models make really stupid mistakes with high confidence. And the problem there is that, so if you think about how EAS works, you generate a solution and then you try to, adjust the network based on the good solutions you see. Now, of course, you should sample your output space. The problem though is that if your model thinks something is really, really bad, like it never chooses that, it's very unlikely that you sample it. So it's also very unlikely that you ever get to see that decision and adjust your model to make that decision in the future. So our contribution here is to try to overcome these mistakes with beam search using simulations to evaluate the quality of nodes. And what we see here as an example is that we have like a confidence mismatch. So A is given a high probability, but D is given a low one, when really, I mean, if we think about like the route here, you can kind of, it's not so clear whether you should go to A or D, and it would probably make sense to try out both, especially if you had like a longer route or more complicated problem. And so the method we propose will allow us to do that. It works like this. There's only 3 phases. It's pretty easy if you're familiar with beam search, but there's a twist. So the first phase is expansion. You expand the highest ranked node. So we're in our search tree here, and we're at this, our beam width is 3. And we're here and we need to expand these nodes and look at the ones below it. So our network is going to tell us that these 6 are the most promising options. We then simulate them in the simulation stage here. Essentially, we're going to do an argmax rollout. That just means we're going to query our network and select the argmax option each time. What's great about this is that this rollout is really cheap because it's a fixed size. It can be done in parallel. Then we're going to prune down to the beam width using the performance of the rollout, right? Instead of what the network said, we're going to use the rollout. Now, what can you do to sort of supercharge this? Because this method itself does really well, but you can actually use EAS every few iterations based on what you learn here to adjust your model. And then that changes, of course, which nodes you see while you search. thus adjusting your model even better. So this is actually really nice in combination with EAS. Obviously, it gets a bit expensive, but it works really well. So let's look at some computational results to start wrapping up here. When we use EAS and SGBS on the CVRP, up here I have the traditional OR method. So here we have HGS, the latest and greatest from Vidal. We have LKH3. Then we have the learned models for the CVRP. I note that this is size n equals 100. So we're doing size equals n equals 100. We've trained on a separate training set. And here we're testing on 10,000 random instances. And over here, I have two larger size instances, 150 and 200, to try to generalize. EAS gets to within 0.35% of HGS. So HGS, again, the best method, hands down. We can't beat it. But we're going to come really close in a moment. So you can see EAS, what's really great is that it generalizes really nicely. Even as the instances get bigger, the gap to HGS does not go up by a lot. Whereas you look at other methods like, so POMO, which EAS and SGBS are based on, the gap goes up quite a bit, and as well as competing methods like DACT. DPDP does pretty well. LKH3, for example, also doesn't really go up that much because, I mean, it's not trained on anything. SGBS plus EAS down here, we get the gap down to 0.2% on the training set, on the testing set. And if you let it run even longer, you can get down to 0.11% after 30 hours of time, which is still less, I know, still less than HGS needs of wall clock time. This is all wall clock. So we are very, very close to the state-of-the-art methods here, which I think is quite nice, especially given the GPU advantages you have when you run these. Maybe I'll skip the flow shop scheduling thing in detail for time. Just note that, again, we have a very, very low gap here. It's to optimality, in fact, very low gap to optimality, which is better than the traditional OR heuristics we have on the flow shop problem, with the small admission that this flow shop problems may be kind of a special problem. So I don't want to claim like we're the best at flow shop in general. Right. So let me summarize, because all those results are online. They're in the paper. Basically, algorithms can be learned for specific data sets. What I showed here, all the code is available, and it's not too hard to use, actually, if you have PyTorch and a GPU. And learned methods have actually almost reached the OR state of the art. I'm going to claim, though, they have on container pre-marshaling. That's one where we beat traditional OR methods quite well, I think. And so I will claim that we've done it on some problems. And on routing problems, we're getting very close. And the way we do it is with search. So if there's one lesson to be taken from this talk, is that search is an essential component of these learning techniques. I know there's some papers out there that definitely cast some shadows on whether search is necessary or good. I think the experimental results that we have in our papers show that search really does a lot to improve the quality of the solutions you get. So if you have a problem where you have the time to do your search, you have time for search, then you should absolutely do it. And there are easy to use domain, essentially problem independent search techniques out there, EAS, simulation guided beam search, that you can bolt on to most of these, pretty much almost any learn technique. I mean, I will say there are some exceptions depending on how your technique is set up, how your network is structured. But for the most part, these are general techniques that you can use anywhere. And they will improve the performance of your model. So I encourage you to do so. And I hope that at least this quick overview gave you some insights into these methods and encourages you to go look at them if you are writing some kind of approach for solving these types of problems using deep learning. Good, then thank you very much. And if you feel free to ask your questions.
Thank you, Kevin. That was a great talk. So I think, Alex, do we want to just move to the breakout rooms? Okay. So
yeah, I think so. And we just wanted to reiterate for those of you who came late that we will have another session next month on March 24th on Friday. So stay tuned for the announcement of that.
Great. So now, Alex,